Afternoon. Sorry, I'm a little slow getting organized here. Okay. What we're going to be talking about for the rest of the week is things that can go wrong in computations that happen in parallel and what to do about it. So to start out, I have to teach you a little bit of 61C. Let's say you say this. Set bang x to x plus 1. Here's what that looks like in a typical machine language. There'll be an instruction that says load, and then a register name, like register 8. That's one notation for it, x. The reason I picked 8 is in the MIPS architecture, the one they use in 61C, registers starting at 8 are used for short-term values that are being loaded in the processor just for a moment. And you'll see why that is in just a moment. And I'm going to say add immediate. Immediate means the thing we're adding isn't in some memory location that's in the instruction. The actual value we're adding is in the instruction. So add register 8, 1, and then store register 8, x. Okay? So that sequence of 3 instructions is what a computer does to add 1 to x. And it goes through that load and store thing because a typical computer, there's the processor over here and the memory over there, and they're 2 separate pieces. So you may have had the experience, for example, of getting a computer and then going out and getting more memory for it. Right? You go to the store and you get a little board that you can plug in that has more memory. And you don't have to change the processor to do that. You just add memory because it's a different piece of the machine. Inside the processor itself, there's a teeny little bit of memory, like typically 32 registers in machines on your desk today. 32 is a very small number, right? The memory of your computer is measured in gigabytes, billions of bytes. And here we have just 32 values. The reason for putting a small bit of memory in the processor is that the registers can be really fast. So there's a trade-off. Again, you'll learn more about this in 61C. There's a trade-off between size and speed for memory. So we have a great big memory that's billions of bytes that's, by processor standards, slow, meaning you can only read or write a billion times a second, let's say. And then in the processor itself, you have a teeny bit of really, really fast memory that during that one cycle of reading or writing the main memory, you might be looking at those registers 6 times to carry out an instruction. Okay? So we take x out of the big, slow memory and bring it into register 8 in the small, fast memory that's inside the processor. Add 1 to the register and then store the result back. Okay? So this is a little load and store architecture, typical of how machines work. Okay, so the problem comes up if we have some form of parallelism in which there are 2 different threads doing things at the same time. So that could happen because you have a dual-core processor, right, which a lot of you do. Who has a dual-core processor or more at home? Almost everybody. Okay. Great. So in your machine, there are these 2 processors independently carrying out instructions. Let's call them A and B. And let's say that A is trying to do set bang x plus x1. And B is trying to do set bang x, I don't know, plus x3. Okay? Now, these happen to be happening at exactly the same moment. So what happens is these things are not just one all-at-once operation. Each of them takes 3 steps: load, add, store. So let's suppose, oh, well, first of all, what should happen? What answer should we get after these 2 instructions have been done? Let's suppose that x has the initial value 100. What should the value be when we're finished? 104, right? We should do both things. Okay, so now what happens? Oh, I should explain, each processor has its own set of registers, even though they have the same memory. Okay, that's how they're able to work independently. So let's say the sequence of events moving down the chalkboard is this. This machine says load register 8 X, and then this machine comes along and says load register 8X, and then this machine says add I register 8-1, add I register 8-1, and finally store register 8X, store register 8X. Okay? So here's time moving down the board. We load X, which has the value 100, into register 8. So register 8 in processor A now has the value 100. Then we load X into this machine's register 8. So its register 8 also has the value 100. Add 1, so that makes it 101. Add 3. So this makes it 103. Store it into X. So X now equals 101. And then store this into X. So we get 103 instead of 104. Okay, by these things interleaving in this way, essentially one of them didn't have any effect. That isn't always the result, but what always does happen is some kind of wrong answer. In this case, the possible wrong answers are 101 and 103, depending on which one gets in there first with the store. Right? It's the order of the stores that really matters. It doesn't matter which load happens first. We get into trouble as long as the second load doesn't come after the first store. So if these things overlap at all, then we're going to get a wrong answer. Okay? Questions about this so far? Yeah. Is there ever a problem with them trying to access the memory at the same time? So what if the 2 load instructions happen absolutely at the same time? One of them wins, probably the same one all the time. The interface between the processors and memory will be set up in such a way that somebody wins. This first we look at processor 1, then we look at processor 2. I don't think it's possible for the hardware to really try and do both loads exactly at the same moment. Okay? Yeah? Is this how you work with local variables? No, I'm envisioning that X is a global variable, or it's an element of an array. It's some shared information. It could be local, provided that the thread separation happens after that local variable is created, because typically threads will share whatever is going on at the time that the second thread is created. Okay? So it doesn't really matter if it's global or local. If each process has its own local X, and they're in two different places in memory, then it won't be a problem. Okay? Yeah, so that's something to emphasize. This is not going to go wrong very often. Okay? A computer can typically carry out 1 billion instructions a second. And that means these two sequences of 3 instructions have to overlap within 3 billionths of a second. Okay, so almost all the time, one of them will completely finish before the other one starts. You might think that's good, that this isn't a very important bug, since it hardly ever happens. But no, actually it's bad, because in computer terms, hardly ever means you might have to wait a day before this situation arises. Because we're going to be running this program over and over and over again, typically. It's not going to be just one thing X that we set once and that's the end of it. This is going to be inside a loop that is doing something or other a bazillion times. And sooner or later, we are going to have this problem. And when we do have the problem, your program is not going to instantly crash. It's not going to say, oops, sorry, 2 things happened overlapping, you lose. What's going to happen is that it's going to compute an incorrect value, and it's going to proceed with that incorrect value, and maybe 20 minutes later, the inconsistency of that incorrect value will cause some other piece of your program to crash. So concurrency bugs like this are really, are really, really hard to find in your code. It's much, much better just not to have them in the first place. So that's why this is an important topic, because especially those, those of you who take operating systems, CS162, or databases, 186, you are going to be doing a lot of things where concurrent operations like this come up. And you're going to have to be able to prevent that kind of bug. Otherwise, you're going to spend really long all-nighters in the lab the night before the project is due, tracking down this bug that only happens once every 3 billion times. Or something. No, I don't mean that. 1/3 of a billion times. Okay? So, it's important that you get this idea of concurrency in your head firmly lodged. And so when you're writing code, you're just automatically going to say, oh, wait, is this a concurrency problem right here? Let me put in a solution ahead of time. And we'll talk, starting now, about what the solution is. So one solution is just never to do things in parallel. Go back to the days of, you only have one processor in your computer. That's not a very good solution. Because parallelism is the way computers are going to get faster in the future. It's not that we're going to have faster processors, it's that we're going to have more and more processors inside your desktop. So a decade from now, you might have 100 processors in your little box, instead of just 2 or 4. And also, parallel computation happens on a larger scale than just the box on your desk. So my favorite example, everybody's favorite example, is airline reservations. Okay? Have you ever had the occasion, ever had the occurrence that you are making a reservation for a flight, and you click on seat selection, and up pops a map of the airplane, and you pick the seat that you want, and then it says, oops, sorry, that seat's taken. Right? Has that happened to anybody? Yeah. Why did it show you that seat is available if it was taken? Well, it was available at the time the computer drew the map, but somebody else was making a reservation for the same flight at the same moment and clicked on the seat before you did. Well, that's pretty bad. You don't get the seat you want. But it's not nearly as bad as if both of you got that seat. Right? That would be kind of a disaster. So the airlines have to worry not about concurrency within one computer, but concurrency across all their servers all over the world. So you can't just say, let's not have parallelism as a solution to the problem. Instead, what you have to do is have the idea of a critical section. You have to say, these three instructions are uninterruptible. Okay, once we've done this load, nobody else is allowed to look at X until after this store. Okay? Now, that's not the same as just saying, let's not have parallelism, because if the other processor is adding 1 to a different variable, y, then they can interleave, and that's perfectly okay. They just can't both be using X at the same time. So this is what's called a critical section. And what you want to do is, in some fashion, before you do the load, you want to say, I reserve X. I have dibs on X. And then you do the load, the add, the store, and they say, OK, I'm finished with X. Somebody else can have it now. All right? Yeah? So what does it mean to say I'm reserving X? It means that if another process is executing either this same code or some other piece of code involving the variable X, when it says I reserve X at the beginning, the system, the operating system, or somebody, the hardware, whatever, will say, no, sorry, you have to wait. And that process will just wait right here until your process says release X. Okay? Oh, yeah, the X is still there. Just nobody's allowed to look at it for 3 billionths of a second. Okay. Let's take a little bit of a look. I'm going to say load CS61A lib concurrent. And then I can show you how this works. So let's go ahead and set up the exact situation that I was talking about on the board. Okay, parallel execute is a procedure that takes any number of arguments, and those arguments have to be thunks, that is to say, procedures with no argument, kind of like the callback procedures we looked at on Monday. And it will run them in parallel. The way this works is parallel execute actually has a little scheme interpreter inside it that switches very rapidly among the different alternatives. So I'm going to say lambda of nothing, sorry, set bang x plus x1, close the set bang, close the lambda, and lambda nothing, set bang x plus x3, close. It says, okay, what's the value of x? Oh, look, it's 103. We got the same wrong answer that we anticipated. Okay, so how do we fix this? And in the book, they provide a high-level mechanism for saying this entire procedure call should be protected against using x. Now, the way you do that, actually, you don't say I'm using x. Instead, I say I'm going to put x back to 100. And then I'm going to say define x protect to be make serializer. So make serializer is the constructor for an abstract data type called serializer. And what a serializer does, it takes a procedure as its argument, and it returns a protected procedure. Okay? So for every variable that might be shared, I'm going to have a separate serializer. So this is x's protector, and there would also be y's protector and z's protector for those other variables. So now I can say parallel execute xprot of lambda nothing set bang x plus x1. Close the plus, close the set bang, close the lambda, close the xprot. And xprot of lambda nothing set bang x plus x3, close, 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 close. And now if I look at the value of x, it's what it's supposed to be, 104. Okay, so the serializer has prevented those two threads from overlapping when they're both trying to use the same variable x. So questions about how a serializer is used? Yeah. Where did I tell the serializer which variable to protect? I didn't. I just used the correct serializer for these procedures. So I looked at this code right here, I, the programmer. I said, oh, this is a critical section with respect to x. I guess I'd better use x's serializer. Okay? More typically, you might have some abstract data type called a protected value that would have two pieces to it, the value and the serializer. So, you know, maybe I would say call car of x with the argument lambda nothing set cdr x to cdr x plus 1. So car would be the serializer and cdr would be the data. You could do that. But the serializer doesn't know, Scheme doesn't know, I, the programmer, know that xprot is the serializer for x. Is that clear? Yeah. What would it look like if I ran a trace on parallel execute? It would be messy, and it would use features of Scheme that we haven't talked about. So I don't recommend it. As far as you're concerned, you're supposed to imagine that there's two pieces of hardware doing these two threads. You can have as many threads as you want, by the way, in parallel execute. They all run in parallel. But what it would really look like is a Scheme interpreter, a little bit like Scheme 1, only more complicated, because it has to be able to switch back and forth among threads. Yeah? Question is, suppose I call xprot on the first func, for the first thread, but I don't say xprot for the second one. Will I still get 104? No. it's the serializer that enforces the fact that only one of them can be running at a time. So if the second one cheats and doesn't use the serializer, then it can be running at the same time. Okay? So they both have to use serializers, and in fact, they both have to use the same serializer in order to be protected against each other. Yeah? He's saying, since there's no real connection between x prot and x, couldn't I use y prot that's supposed to belong to y to protect x? Yes, you could, but then what you're doing is preventing a thread using x and a thread using y to run in parallel. Okay? Once you do that, you might as well just not allow parallelism, period. So basically, what you have to imagine is you and your spouse have ATM cards for the same shared bank account. Okay? Now, a bazillion other people have ATM cards for other accounts at the same bank. And people are constantly using ATMs all over the place. So if you and your spouse happen to show up at the same time to do a transaction, it should make one of you wait. But if you and I, with two different bank accounts, show up at the ATM at the same time, it shouldn't make one of us wait. Okay? So you want to have just the right amount of protection. Not too much, not too little. We'll get into the topic more in a second. Yeah? So if instead of using xprot, I had said make serializer here and also make serializer here, then I'd have two different serializers, and they would not mutually exclude each other. So no, it has to be the same one. And now it could be a let, so it could be local, but that kind of defeats the purpose. You really want it to have the same scope as the variable it's protecting. Right? Okay, let me move on. Okay. So we actually have a set of abstractions about serialization. Looks like this. Here's my abstraction diagram. So this is make serializer up here. And this is something we'll talk about in a moment called make mutex. And these things separate the levels. So at the bottom is atomic, test, and set. So we'll see that in order for this protection to work, you have to be able to load the value of something and store a new value at the same moment. That nothing can get in between the load and the store. Okay, so you're like exchanging values between the processor and the memory atomically. So test means you have to be able to look at the thing. Set means you have to be able to set it. This isn't being used for x. It's going to be used for x prot up here. Okay, so atomic test and set is typically provided by hardware in some form. And we'll talk a little bit, but not very much, about how that works in different situations. For right now, what I want you to see is when I was showing you what the set bang translates into, I said, we want to be able to say at the beginning of this, I reserve X, and at the end, I'm releasing X. Somebody else can have it now. As two operations, the start and end of a critical section. That's not what I showed you with Make Serializer. Make Serializer, the start and end points are implicit. And what I'm saying with the serializer is protect this procedure call. Okay? So a serializer is a more abstract mechanism than the mechanism that says, I reserve X, and now I'm releasing X. That mechanism is called a mutex. The word stands for mutual exclusion, right? Because these two processes exclude each other from using X. So make mutex uses atomic test and set, we'll see how that works in a bit, to create something called a mutex, and that gives you critical sections. This level of abstraction is typically provided by your operating system. So on your computer, you're running, looking around the room, Mac OS, or maybe you're running Linux, or maybe you're running Windows. Each of those systems has a mutex mechanism in it. So you can say, allocate me a mutex, and then you can say, start of critical section for this mutex, end of critical section. You may have heard, and if not, you will in the literature, the name semaphore for this level of mutual exclusion. A semaphore is like a mutex. It's a little more complicated because it has the ability to let exactly 3 processes use this resource, but no more than 3. So the first 3 acquire the mutex operations would succeed, and then a 4th one would fail. Why on earth would you want something like that? Well, you wouldn't in a situation involving reading and changing the values of variables. But let's say in the lab there's 3 printers right next to each other. And you want all your different computers to be able to say, okay, I want to print a document. You don't care which printer it goes to. So the first 3 people who want to print something win, and the 4th person has to wait until somebody finishes printing. That's the kind of situation where you would want a semaphore. People hear the word semaphore more than mutex, because semaphore was actually invented first, I think. That was the beginning of thinking about critical sections. By the way, everything that I'm telling you now was well understood by computer scientists in the late 50s, I think, mid-50s. Despite which, it's only quite recently that operating systems are more or less free of concurrency bugs. So those of you who have Windows computers, if you're old enough, you may remember getting, in the old days, the blue screen of death fairly often. Fairly often meaning once a day or so. Right? That's in the pre-Windows NT Windows systems. Mostly the reason for that was concurrency bugs. And the same was true of the Unix kind of systems and Mac systems and everything until maybe the 70s or early 80s. All of these systems were full of concurrency bugs because the people writing the operating systems were not the computer scientists who knew about this. Because in those days, remember, you couldn't major in computer science. Like when I was in college, I was a math major, even though what I really majored in was programming computers and being a disc jockey. But technically, I was a math major. And I never heard anything about concurrency until much later, except in certain ad hoc situations where I would know about certain things that had to be protected. Okay, so operating system gives you the ability to delimit a critical section with a beginning and an ending, and then typically you would have a protected procedure. Oops. Or you might have a protected object. If you're programming in an object-oriented language, an object, you'll recall, has a collection of methods for all the different things it knows how to do. And a high level of abstraction for serialization might be only one thread at a time can manipulate this object. So all of the methods of the object would be protected by one serializer. Okay, that's a fairly typical thing to do. And that level of abstraction is provided by a programming language. Okay? None of this is cast in concrete. So you can take atomic test and set and invent serializers directly on top of that. These three levels don't have to be hardware operating system programming language. They can be, the work can be divided up in some other way. But this really is pretty typical of the way modern systems deal with concurrency. Okay, questions about the picture? Okay. Let's see, where are we now? Oh yeah, the book characteristically works its way down. It starts by showing you, as I just did, here's the feature we want. We want serializers. And then it says, okay, how can we make serializers? We make them out of a mutex. And how do you make a mutex? You do it out of atomic test and set. It's almost but not quite true that you must have some kind of hardware support at that lowest level to provide the atomic read and write operation. It's not quite true. You can look up, you can Google it if you're interested, a way of doing concurrency control that's entirely implemented in software with no hardware support except the usual, add, subtract, load, store kind of operations. But the algorithm is pretty complicated. Convincing yourself that it really works and why it has to be complicated in just this way is even harder. And as far as I know, nobody actually uses it in practice. It's one of those things that, you invent for your PhD thesis, and everybody says, isn't that nice? And they go on doing things the easy way, which is to have some hardware support. The hardware support is not necessarily a machine instruction called test and set, as it is in the simulated system that the book talks about. For instance, if we're talking about internet scale parallelism, like you're the airline, and you have these servers all over the place. It's not just one server, there's a bazillion of them, and they have to stay synchronized. The atomicity at the lowest level turns out to be provided by networking hardware that makes sure that two packets coming into your computer can't step on each other at the same time. That just keeping the packets separate is the basis on which we end up providing atomicity. Okay, so that's very different from looking at one particular location in memory. There are other kinds of low-level support for parallelism too. I don't care that much about the low level. I care about what we build on top of it. Except, I guess I should say, in the old days, when I was your age, there was hardware support for parallelism, and it was a very primitive kind. Basically, it was, okay, turn off parallelism altogether for this block of code. So you would, instead of having a critical section regarding the variable x, you would just have critical sections, period. And since sometimes the things you want to do in a critical section are long, that's not so good. You don't want to sort of turn off time sharing, the ability of the computer to do different things at once, for a long period of time, not even long in computer terms. And so what you would do is you would use that primitive turn off parallelism altogether mechanism to invent a guaranteed atomic test and set on which you would build mutexes and so on. Okay? So these days we have better hardware support, but in the early days of thinking about it, they had a much more limited kind of hardware support, and we're still able to get the job done. Used to be back then, by the way, well, it's still true, actually, that operating system programmers get paid more than all the other programmers because they have to understand this parallelism business. That's starting to change. Nowadays, everybody has to understand parallelism because application-level programmers are creating threads and have to not step on each other's toes. So now everybody has to understand it. But it used to be that only the operating systems people really understood anything about parallelism. Okay. All right. So when we have concurrency, the last thing we're going to do today, and we'll continue this Friday, is talk about 4 different ways that things can go bad. And they are incorrect results. That's the worst case, right? That's we get 103 and we should have gotten 104. By the way, what counts as a correct result? When 2 programs want to modify the same variable and lots of different outcomes are possible, how do we decide which outcomes are okay and which ones aren't? Answer. The result must be consistent with some sequential order of carrying out the operations. So you can do things in parallel, but you have to get the same answer you would have gotten if you didn't have parallelism. If you did this thing and then you did that thing separately. Now, that still might be more than one possible correct answer. So if instead of adding 1 to x and adding 3 to x, we say add 1 to x, and the other one says multiply x by 2. Okay? Let me come over here and do that. So one of them is computing plus x1. The other one is computing times x2. Okay. And x starts out at 100. What if we do this one first, then that? Okay, 101, 202, right? What if we do this one first and then that? 100, 200, 201. Okay, so these answers are correct. The possible wrong answers in this example are 101 and 200. In which effectively one of them happens and the other one doesn't happen. That's that interleave situation we saw over here. Okay? So there isn't just one correct answer necessarily. There could be several correct answers and several wrong answers. We have to get a correct answer. So incorrect results, that's the worst thing that can happen. It's better that your computer crash than that it give you a wrong answer. You may not think that's true. I mean, what's one wrong answer now and again? But the wrong answers sort of build up on top of each other over time, you get wronger and wronger and wronger, and eventually you really get in trouble about it. Whereas if your computer crashes, you figure out what the bug is and you fix it, and then everything works well from then on out. Unless your computer is running a telephone switching system. It's the computer you talk to when you pick up the phone and get a dial tone. For those computers, getting an occasional wrong answer, meaning every once in a while connecting you to the wrong telephone, is better than the system shutting down altogether for everybody. Right? But for most computations, incorrect results are the worst thing that can happen. Next one is inefficiency. A particular inefficiency. Yeah. A particular kind of inefficiency, the one in which we fail to do in parallel things that could be done in parallel. So that's if you just have one serializer protecting everything. Right? So not only can't you and your spouse use the ATM at the same microsecond, two people, it's as if there's only one ATM in effect in the whole world. So that's not good. The third one we're going to talk about is an interesting problem called deadlock. This comes up, I'm not going to give you the details in 2 minutes, but here's the general idea. This comes up when you have two different threads, and they both need to use X and Y. Thread A acquires X, thread B acquires Y, and then neither one can proceed until the other one finishes. That's a deadlock. Also sometimes called deadly embrace in the early literature. And finally, this is too short a name for it, but this is what I call it in the notes, is unfairness, in which process A always wins. Okay? Now, a little bit of unfairness is not a terrible problem. If process A wins more often than process B, so what? But if process A keeps requesting resources over and over and over again, and process B never gets to run at all, that is a problem. So we have to make sure that everybody gets a turn once in a while. Okay, we'll talk more about these things on Friday. See you. Oh, and don't forget dim sum Saturday.